collaborator of the Haiti Lab. So thank you for joining us.
All right.
It usually takes a second to turn on. I'll try. Yeah.
Is it working? Okay. Okay. Hello, everyone. I'm so happy to be here. Before we begin, I would like to tell you this. Even if you see my hands holding this mic shaking, don't worry. I was hugging my baby until 3 a.m. last night. She didn't sleep. And then I put her to sleep and decided to drove here. Came here 5 a.m. and then slept in the patient parking lot and came here. So I do not have any medical condition that you should be concerned about, okay? Yeah. All right, so this talk is really about some basic statistic for machine learning. That was our intention. And I found a lot of materials are covered by other great invited lecturers. So I actually trim down a couple of materials like during the lunchtime. So let's just begin. I think statistical machine learning may sound a little too boring, so I kind of renamed it. Okay. So today's session name is Encyclopedia of Common Statistical Mistakes. How does it sound? Sound more interesting, right? So I'll start with the part one, which is common statistical mistakes during pre-processing and missing data imputation, variable selection, and imbalanced data set. And during the model training, I used to have a couple of them, but I found out it's overlapping with the Tarshis session, so I trim out a little bit. So I'm going to cover only one thing, the benchmark and selection of predictive models. And next, we're going to look into common mistakes during the model evaluation. I think most common mistakes are actually coming from this part. When you evaluate your model, it's hard to be objective because it's your model, and if it doesn't work, then you are in trouble, right? So I'll cover a couple of common mistakes that I've seen from papers as a reviewer, also from my student, and also from myself. Okay. And lastly, this is somewhat not precisely the part of the model building, but I wanted to incorporate it because this is AI bias datathon. Okay. So we'll cover a couple of statistical mistakes for disparity analysis. And I'll show you what is common mistakes out there and what we've been trying to address it. Okay, so part one is common statistical mistakes during pre-processing. So let's just jump into it. I'm going to start by introducing some basic concepts and then move on to the mistakes. So let me start talking about missing data. I think missing data was already covered during the very first talk, but I would like to cover this from statistical point of view. Okay, so when it comes to missing data, you actually need to know those two terms. One is MCAR, another is MNAR. Okay, MCAR stands for missing completely at random. Okay, and MNAR stands for missing not at random. Okay, so this matters the most when you deal with the missing data set. Okay, and which one do you think will be easier, MCAR or MNAR? Anyone have any idea? What will be the easier one to deal with? Missing at random or not at random? Anyone? Missing at random. Okay, that's interesting. Okay. Based on my response, you know that most of you got this wrong. Okay, so yes, Judy, you got it right. From statistical point of view, MCAR is easier to address. Okay, because the remaining data set, those are not missing, actually can be used better and generalized better to the missing ones. Okay, if it's missing not at random, then those you have in your data set cannot be generalized to the missing part. Okay, so for example, one of the example I put here, depressed patient would not likely to answer a questionnaire, are you depressed? Because they're depressed. Okay, if they're missing in your data set, and those who are remaining in your data sets are not depressed, then it's really hard to figure out your missing part. So again, statistically, M-CAR is easier to deal with than the M-NAR, okay? And there's no way to distinguish between those two, okay? It's really, you are actually entering the gray area when you're trying to justify that those missing observations, you think those are M-CAR, okay? So, but at least you should be aware of this and then try to address in your paper if you ever write paper after missing the imputation, okay? Okay, so one statistical method to address the missing data is imputation, and the one that I brought here is the statistical one. So there's a statistical imputation using regression. If you see the table on the left side, there's only one missing value, patient 3, sugar intake. And how do you use regression to impute this data, this missing point? Okay? I'll just give you an answer because it's simple. You put sugar intake as your dependent variable and other column as your independent variable. Use patient 1, 2, 4, 5, 6 to build up the regression model. Use that regression equation. Plug in the glucose level of patient 3, patient age of patient 3, carb intake of patient 3 into your regression model, then you will be able to calculate the missing value using your regression equation. Okay? Sounds easy, right? Because whenever I cover this in my lecture, my students think it's so easy. Well, in real world, it's not as simple as this. So if you see one on the right side, the problem here is there's a missing pattern. Okay, it's not like a one particular data point missing. There's some pattern here. Anyone want to try? How are you going to use regression to impute this? I mean, which column and which patient are you going to use to build up the equation and then fill up the missing part and then move on to the next missing value? Any idea? There's no answer, by the way. Okay, so you're going to use sugar intake and the age. So those are the missing ones. So you're going to build up the regression model with the patient 1, 2, 5, 6, because they are not missing, with the what columns? Glucose and carb intake. Okay, that's good. Then with that equation, you can find the value for the missing for patient 3, right? But what about patient 4, right? So it actually gets complicated. Yes. Mm. Yes. Mm-hmm. Yeah, that's totally possible. It just requires a couple of steps, like which to fill up first, which to impute first, and then move on to the which one. So are you going to target the patient 3 sugar intake first, or are you going to target sugar intake column first, or which first? So those are really complicated. Even with this small data set, it's already complicated. If you have thousands of patients, it's virtually impossible. Okay. So the common one being used, I brought here is the mice imputation. I'm going to share with you the code at the end of this session. The way it works is that you see the A, B, C, there are 3 columns here and multiple missing values. You start with some arbitrary value. You just put in some not completely random value. I may just use the mean imputation. You take the average of the particular column and use that value to fill it up. Okay? Then your column is complete now. Now you use all the patient in column B and C, okay, to build up the regression model, and go back to the column A where you fill up the impute the missing value, update the value. Next round, your target is column B. Use the column A and C to build up the regression model and update all the missing values in the column B. And then you do the same thing for C. That's the one iteration. You repeat the iteration over and over again, then you converge at some point. And that's how you can use regression to impute those missing values. So that's how mice works. And reason I am introducing you how mice works is it's pretty decent method. You can use it, and no reviewer will reject your paper for using mice. So it's generally well accepted method for imputation. Okay. Okay, so that's how imputation works. You gotta be careful. Imputation distorts the distribution of variable. Okay, if there's a bias, then you are amplifying your bias. Okay, so that's the heads up. I got the most straightforward and simplest possible example here. If you use a mean imputation, means that you just use the remaining patient in the column and calculate the average, and use that value for imputation. You can see for carb intake, patient 4, 5, 6, 7 have the same carb intake after imputation, right? And that will amplify whatever bias sitting in your data set if there is any, okay? So that's just simple example, but I just wanted to give you a heads up that it can distort the original distribution, okay? So caution, caution required here. Okay, so feel free to ask me any question. This is it about imputation, and let me move on to the variable selection. Okay. There are many different methods out there for variable selection, but the one that I brought in here is one of the most popular one these days. Okay, so you know there's an unsupervised clustering method out there, right? I think it was also introduced in Satoshi's session. Okay, there's an unsupervised uh, classification algorithms out there. You have a patient data set like this, and then let's say you are grouping them into two different clusters, and somehow your cluster is looking like this. Group 1, there are patient 1, 5, 6, and group 2, other patients. Okay. Basically, you're using the same algorithm, but you do the transpose of your data. What does that mean by transpose? You're just flipping your data diagonal way. Okay. After flipping, now each column is not variable. After flipping, each column is patient. After flipping, each row is not patient, it is variable, right? So now you have a patient in your column and row in your, the variables in your rows, okay? You do the same unsupervised clustering, okay? Then instead of grouping patient, this time you group the variables, okay? Now you assume that they're in the same group because they are similar. If they're similar, you only need one of them, one best one among those. Okay, so that's the idea behind many of the automated unsupervised variable selection these days. Yes.
In your second example there, does the scale of those variables matter if they can be clustered? So if glucose level is in the hundreds, but carb intake is like 5 grams, 10 grams, does that matter if the scale is different?
I believe it's scale insensitive because it's basically geometric. It's like some, you can imagine like coordinate system. They're just each data point is each coordinate, and they're just tied into the same group. So yeah, but I'm not 100% sure. Yeah, may need to look into it. Yeah, but I believe it's scale insensitive. Okay. All right. So this is there are many different versions of, like, basically if there is unsupervised clustering algorithm, you can just apply it to this case for variable selection. Just any unsupervised clustering algorithm can be used. What are the mistakes? Mistake here is do not rely on it too much, or do not trust it actually. Yeah. You have to be very suspicious about the result. Okay. So like I said, please be sure to consult with your someone, your physician or someone with the domain expertise after running this. Okay. Examples I have here, those are from postpartum hemorrhage prediction. It may not be that intuitive to you, but the first one may be intuitive to you. Okay. So whether there's going to be postpartum hemorrhage or not, and your independent verb, your predictor has a normal delivery, whether it's normal delivery or not, how can you possibly use this model in clinics? Because you cannot use it until you have this value, and this means that you cannot use this model until normal delivery happens. By the time normal delivery happens, postpartum hemorrhage will happen together. You see what I'm point? You see my point. So those have some issues in terms of time points, and those also limits the usability of your model. So those are the variables that we took out from 25, 30 variables after sitting down with the clinician and went through one by one, and we manually exclude those out after automated selection. Okay. All right. And also, it was emphasized many times in previous sessions, be careful with the ICD codes. And also, I would like to remind you that those are for billing purposes. Okay. In case you don't know what that means, it can mean something serious when you use that for building up clinical models. Okay, because it's for billing purposes. And so in my lab, my students and I, we use one hotkey coding, just like Septarshi mentioned. But whenever we submit some work, I think one of the most common criticism we get from reviewers is, why don't you guys use embedding? And those of you who know what embedding is. And we are kind of against it, because if you use embedding, then those information will be lost and your model will be less explainable. That's my personal biased opinion. Okay, so if you're interested in this comment, come to me after this session and we can have a very long, great, interesting conversation. Okay. Now let's move on. Imbalanced data set. I think a lot of mistakes are being made when people are dealing with the imbalanced data set. And here's the introduction. The postpartum hemorrhage data set from NIS, the National Inpatient Sample, is imbalanced. Okay. So if you see here, you see there's a PPH only happening 2.73%, and non-PPH is 97.27% in total. Okay, this is very imbalanced. What does this mean? If your model always say no PPH as a prediction, what's the accuracy your model is going to get? Anyone? Yes, you don't need even math. You can just read that number right here. 97.27% will be your accuracy. Okay, so that's what makes it really tricky. And what's the definition of an imbalanced data set? I get this question a lot. In statistic textbook, it says 5%. Okay, but it really depends. Okay, so while textbook is saying 5%, I think you will start experiencing some issues and challenges when minority class drop below 10%. Okay, if it's 9%, 8%, 7%, you will start running into challenges. Okay, and just let you know, you are dealing with a completely different animal here. Okay, so the existing model may not work well. Existing technique may not work well. There are people who does only doing research on imbalanced data set for their life. Okay, and there's a model just for addressing imbalanced data set. There are techniques just for dealing with the imbalanced data set. So you have to be very careful. Nonetheless, there's one most common technique being used among people out there, which is oversampling, undersampling. Okay, undersampling is easy. You have, how many pph do we have? We have a 179,210 pph. You just randomly undersample the non-pph and make the same ratio, 50-50 ratio. Okay, that's undersampling. Please do not do that. Okay. Yeah. There are better methods out there, I'll say. Yeah. But that's well, I mean, if it makes sense to you, I mean, it's better than not doing anything though. I mean, because if you do that, then your model will not say no PPH for all people. Okay, it will say PPH for some people, and that's an improvement. Okay, but you can make your model more sensitive. There are some methods out there, so you can use it. let me correct myself. You can use it, but there may be better methods out there. Okay. Okay, so that's undersampling, but I would like to talk more about oversampling, and specifically, I want to talk about SMOT. It stands for synthetic minority oversampling technique. What does this mean? It's just creating fake data set, fake positive cases based on cases you have. Okay, so here you see the dot in the orange color are minority classes, and after creating small, you can see it creates some synthetic data set, fake data set, using the points, existing points, and that kind of creates the some connections between lines. But that's just the idea. Okay. And so smooth is okay, but the problem of smooth is that the people rely on it too much sometimes. Okay, so smooth can amplify bias in your data set as well, just like imputation. Okay, so I cannot really go too deep into it, but let me just give you the big picture. Um, inside this inside this PPH cases, which is only 2.73% of your data, there may be some underrepresentation of certain population. If you use smooth, then you'll be amplified. Okay. For example, some patients are missing for reason and not captured as a PPH here. If you use a smooth to amplify it, then that can worsen the bias. Okay. And this is just maybe off the topic, but one of research that one of my students doing is doing smooth, but try to be try to consider different aspects of those underrepresented patients. Okay, so not just create the synthetic data set because person has PPH, but trying to consider who are truly underrepresented inside the PPH group and trying to perform smooth based on that. So that's one of the things that it's very preliminary things that we are trying. Yeah. All right, so that was the part one. Any questions before we move on? Yes. Yes, great question. When you perform smooth, there's no limitation. So you can actually make it 50-50 when there are a million non-PPH cases and only two PPH cases. If you use small, you can make it 50-50. So it really, it's really tricky to, because people would just, without thinking, make it, use small to make it 50-50. And that's actually may not be the best practice. And to what extent you should oversample to like make it generalizable is a really tricky question, I think. Yeah. So I would say it depends, and I don't really have answer. I mean, is that what you asked me, or does it make sense? Yeah. Okay. All right. And I personally like this one. So start with the situation. There are 14 competing AI tools for breast cancer detection, and 14, that's ridiculous, you know. We should make a one universal one, and now there are 15. So, yeah. So I'm actually guilty here. All right, so moving on. So there are a lot of models available out there, and you have a variety of options. And just as Satoshi mentioned, I think the most popular one these days is the boosting-based one. Okay, so there's a light GBM introduced, and also XGBoost. Okay. Some people, actually quite many people, were still trying to use the neural network-based one, such as Tap Transformer, suggested by NVIDIA, and TabNet, suggested by Google. Those are, there are so many papers saying, oh, TabNet's better, or XGBoost is better, Tap Transformer is better. There are so many papers like being published like every day, but I think it became more obvious in the year of 2024 that the XGBoost or boosting-based method are actually winning, beating the neural net-based models. Okay, that's general trend that I'm seeing based on papers I read. Okay, so the reason here, I think I put it in the bullet point 4. It's actually quite biased, personal opinion. I think neural net-based models are harder to train, harder to configure, optimize, and boosting models are relatively easier. I will not say too easy, but it's easier than neural net models. And that's why a lot of use cases, XGBoost or boosting-based based models are beating the neural net-based model. But it's just my suspicion, and I don't have any supporting evidence. Okay. So what's the common mistake? The most common mistake in predictive modeling using machine learning is to use machine learning. Okay. I know it sounds weird, but a lot of cases, use of machine learning model is overshooting. based on my own biased experience. Okay, you will get some performance gain, but not drastically more, and to the level that you give up all the explainability of existing traditional model and move on to the machine learning model. Okay, and kind of bullet point 2 is kind of echoing what I just said. If you carefully craft the traditional model, such as even a simple linear regression model or some simple decision tree model, you can sometimes outperform those fancy models out there based on many of my experience. And not only just in healthcare, but in other data set I deal with finance and some other data set, I think this can be true quite frequently. Okay, and last mistake I would like to mention is again, you do not talk to someone with domain expertise. That will be the biggest mistake. One of the paper I recently reviewed says we develop an AI screening model to detect asymptomatic COVID-19 patients using CT images. Can anyone tell me why this is? Yes, go ahead. Yep, yep. hmm That's one good point. Yeah. Yeah, yeah, yeah. And this, uh, how do you think about this study objective that they mentioned in their paper that we develop a AI screening model to detect asymptomatic COVID-19 patients using CT images? So that's actually one of the papers I reviewed recently. And what bothered me was actually the screening too. I mean, you cannot use CT as, imagine everyone taking CT scan of everyone, like you think they may or may not have COVID. Okay, so even if it has high accuracy, it really cannot be used, I think, to general population. Like they should not say screening, or they may want it to. They should have limited the scope of the use cases, such as maybe in hospital, you can um, you can prevent the in-hospital transmission from asymptomatic patients. So those are kind of things that I see sometimes that their use cases or application or objective don't really make sense to me. So yeah. Okay.
This is, I want to pause here for 1 second because this is an important point. Anybody have any other reason? There's many reasons this is a bad idea, not just one. So, anybody else have any ideas? Okay, so between hospitals, the device could be different. So, generalizability problem. Okay. Yep. That's exactly what Dr. Wu's point was, asymptomatic patients. So, CT is generally not a good screening test. What else? Who's getting CT scans? Sick patients, right? So sick patients are getting CTs. They have lots of comorbidities. What do we know about COVID-19 in terms of how it manifests in different people? I mean, does everybody experience COVID-19 the same way? No, right? For the non-radiologists in the room, which is pretty much everybody except me and Judy, the imaging, this is the other problem. The imaging findings of COVID-19 are very, very non-specific. So they overlap a lot with other diseases. And so as a radiologist, during the pandemic, the most we could say on CT or X-ray was these findings can be seen in COVID-19 infections, but are not specific. So you got tons of patients who were COVID-19 positive, had no imaging findings. You had patients that had imaging findings that could be COVID, but could also be TB, not TB, but other viral pneumonias. And then you had patients that had COVID-19 who had totally atypical imaging findings. So there's many reasons that this sort of clinical question, the test is the wrong test, the patient catchment is the wrong patient catchment as well. I just want to highlight that. Ends up being the downfall of a lot of model building is, again, not arriving at the correct clinical question.
Thanks. Yes. Huh? Yes, yes. So good question. Like, what do you mean by carefully crafted? And I said in many cases, what are those cases, right? So tabular data set uh, is simplest form of data set in terms of complexity compared to image, speech, or text. I think unstructured text, and a lot of cases is captured with in a way that it doesn't involve complexity. For example, one of the traditional breast cancer screening model, tabular tabular version of it was had a classification in the tabular Excel spreadsheet. There's a classification, there's a density, there are other variables there, right? That kind of data set, I believe even traditional statistical model can definitely classify um, the patient correctly. So, um, and some some tabular data sets are obviously complex, and you do need a more complex model with the more flexibility. But most of the majority of tabular data sets I've been seeing is actually may involve some cleaning or specific transformation task. But after that, in terms of model architecture, the traditional model can perform pretty well. I am sometimes surprised. Yeah. So yeah, that's what I meant. Yes. Yes. Yeah. Um, I should have deleted this column. Dispar- disparity score is actually our own way of multivariate way of evaluating the model failure. So I'll get to this, but the entire idea is that we are not uh, stratifying AUC by race or gender or anything like that. We actually built up another descriptive statistical model to see who are truly, what are the truly the, the variables associated with the model failure. And based on that, we quantified the disparity score. Yes. So it's actually in our paper. Soon it will go to you for review, by the way. Okay, so sorry for the oversight. Okay. And the last thing is that if you're going to use machine learning models or actually any model, you will need a benchmark to justify your selection, especially if you're trying IEEE conferences for publication. You must have benchmark, otherwise you get automatic rejection. Okay, and be careful when you compare boosting-based model with the neural net-based model. Okay, a lot of people, a lot of the papers out there about oh, neural net is better or boosting is better, they're really comparing like apple to orange, you know, because they are too different, and depends on how you pre-process it, depends on how you tune it or whatever it is. It may not be a fair game to compare those two. And if someone's suggesting their own method, it's actually totally possible to do cherry picking. Okay, so as a reviewer, I think I'm very confused sometimes whether this is really true or is it just unfair game that is flavor of their own proposed architecture. So that's just my 2 cents. And type of paper that I am most cautious is the when they propose their new method, and along with that they propose their own performance evaluation metrics. That's a red flag to me. Okay, so yeah, sometimes it can be justified, but just make sure you ask for the uh, the the result from the conventional metrics as well. Okay. All right. So part three is the mistakes during model evaluation, and in this cartoon, there's nothing wrong with it actually. Yeah, you can pick up the threshold and then you can figure out what will maximize your F1 score or accuracy or whatever. The problem is a lot of people are doing that over a test set. Okay, that's cheating. You should have done it using over validation set. Okay, so if that makes sense to you. Okay, I will not go too deep into it, but there are a lot of performance metrics, and well, this is the same data set, different model, different metrics. Okay, and depends on what metric you use, you will see different rankings. Okay, so this is why I'm saying it's easy to cherry pick. You can just pick up the metric that is favorable to your proposed method, and it's totally possible your model is the best model. Okay? So that's the first thing I would like to mention. Second thing is that if you are by any chance undergrad or don't have much background in machine learning, you should at least know what accuracy means, F1 score means, and AUC means. Okay, so that's my homework if you do not know those three metrics, because those are the most common ones. And there's a metric with the trade-off relationship. That's also basic statistic. Precision and recall depends on how you set the threshold. You can maximize precision or maximize recall, but you cannot maximize both of them. Okay, yeah. And again, imbalanced data set. I think we cover pretty much most of it, so I will not go too deep into it again. But again, if your model's not functioning, but if it's imbalanced, then it is possible to achieve high accuracy and actually also high AUC as well. Okay, yeah. This model will not give you AUC of 0.5. Okay, so it may give you higher than that. So just be careful. Okay, and this is again more clinical question, but if this imbalanced data, actually a lot of imbalanced data set is more like a screening models. If it's screening models, then you may want to pay more attention to sensitivity. Okay, sensitivity I think is recall. Yeah. Okay. Next thing is the absence of failure analysis. I see this a lot from many papers. Your AI cannot be perfect. It fails time to time, and make sure you look into a couple of cases even manually or come up with some method to review those failures, like what will be the cause of failure. This is just from my own paper. It measures the size of it performs the treatment response evaluation by measuring size. And you see there are 2 points on the top, 2 points at the bottom. Those are failure. The difference between human and my proposed method is huge. So I manually pull out those 4 cases and kind of visualize it. So this is what I did in my paper. And not sure if this is the best example, but at least show some effort that you are mindful of those failing cases and you did look into it. Okay. Yeah. Lastly, this is actually from one of my students' assignment submission. Okay. I didn't ask for permission, but it's not just this student. I get this kind of assignments a lot. You see XGBoost trees and TabNet, DNN. What is the precision of 0.98, recall of 0.97, F1 of 0.98, accuracy of 0.98, AUC of 0.99. Okay, this is not result. This is error message. Okay, you should consider this as error message. If you see those methods, then it's one of those 3 cases. You have a reverse causality. Okay, you have a data leakage, or you have overly simplified task with a trivial solution that does not worth machine learning, or you deserve Nobel Prize. Okay, so it's one of those 4. Yeah. Yes.
Can you explain reverse causality?
Yes. So one of the example, I think I put it here. Yes. Yeah. So imagine you are predicting length of stay in hospital or ICU, and one of your predictors is amount of charge, how much you got charged. Okay, that's a reverse causality because you normally get charged or billing after you got discharged from after your hospital stay, then now you're using that charge for predictor, then they are violating and they're highly correlated. This will give you 0.99 AUC actually. Yeah. Yes. Yes, please.
So this past, I think it was 2 weeks ago, some of my PhD students and postdocs were evaluating a model to predict relapsed opioid use disorder. And some of the students, we used a training set, a validation set, and a testing set. And we saw a table like this, and in the training set, we were getting accuracy for a couple of the models closer to 95, 98, 99%. But in the validation set, we saw accuracy 0.8, 0.85, okay? And I said, and I told my students this, don't pick the most accurate model. Pick the model that's got one of those accuracies that's the closest between the training set and the validation set, because that's telling you that it has the best chance of extending and performing in the test data set and in production. So if I see something like this with a 0.99 AUC in the training data and a 0.6 in the validation data, it's a huge red flag that I've overtrained the model, and I say, nope, that one, we throw that one right out. I will pick a model with a 0.85 AUC if it's got a very similar AUC in the validation data set, because I've got stability between the training data and the validation data, and I think that that's going to give me a chance to have stability once I get into the testing data. Thank you, Professor.
Thank you. And let me tell you something hilarious. Those numbers are from test set. that's it. Yeah, I know. Yeah, that's another thing. Yes, yeah. Actually, they pick up the best model from using validation set, and then test set just running for the last time for different models. And yes, choice of model from here is actually another violation. That's a really good point. Yeah, because it's like your model's indirectly exposed to test set by picking up the best model. So yes, that's another good point. Yeah, but I don't even expect that much from my student. But this number is just, yeah. I see this really frequently, by the way. Yeah. All right. So last part is about, I'll just make it really quick. Common mistakes during the disparate analysis. I see this mistake a lot. Not sure if it's appropriate to call it mistake, but to me, it looks like mistake. So during the last year datathon, a lot of presenters mentioned this kind of pulse oximeters like being inaccurate against certain population. So here on the left, this is the biracial group. On the right is showing you, actually they have a result as well. Maybe I should have brought that result. Depends on tone of skin, not just like bright or pale or dark, but they got a scale of it, and then found out inaccuracies somewhat related to that as well. So my question is, will they also be inaccurate for white patient with darker skin tones or black patient with the lighter skin tones? How do you think? I may not have that data. Yes. Yeah. But just by the fact that you are not sure means that you need a multivariate approach here. Okay. You cannot just say it varies by, when you just stratify by racial group, and you cannot really say that it is race. I mean, yes, it is correlated, but it does not really tell you that that's the underlying factors. Okay, so that's why we are trying to do some multivariate approach. We are still working on manuscripts, and well, got rejected. It's not very well accepted. Yeah, gotta try again. Yes, that's life in academia. Um, So if you see the univariate p-value, it's just you can imagine just plotting performance by by different racial group, different age group, or different densities, and you will see in most cases they are significantly different. Okay, Moment you have everything in your model and take the multivariate approach, you see some are still significant, but a lot of them are not significant anymore. Okay, so that's what I'm saying. Your model should have exposure to all those varying factors so that it can make a holistic analysis on what's the cause of your failure. And we do the same thing for the NIS dataset with the postpartum hemorrhage model. You see some are significant, some are not. Actually, many of them are significant. It's, it's also partly because we have a lot of patients in our data set, but still this is, I think, more desirable approach than univariate. Just simply plotting different AUC by a different racial group or a different age group. This is the approach that we are trying these days. So with that, I would like to thank you for listening. And after this presentation, I think this is already up. I kind of outlined the general standard flow of building up the XGBoost model using some public open data set. So you can play with this script and also play with the data set. Yeah. Okay. Thank you.
Thanks, Dr. Wu. That was fantastic. Any questions? Yes.
The 0.99, the results that you were seeing with the test set, like, are you saying that if I have like these results for the training and the test sets, it's not something that you should consider as a good model?
So you said training and test set. So
with the AUC and the F1 score and the precision. Yes.
So first,
Yes. So I was asking that. So this was on the test set.
Yeah.
The confusion matrix was on the test set. So my question is, why, like, if it was on the test set, that is it that you had poor training accuracy? That is why you said this model wasn't good, or you like just like someone explained that if you have a training accuracy of 0.88 and a test accuracy of 0.8, that is better than having like a training accuracy of 0.99 and then having 0.8 validation accuracy.
yes, got your question. I cannot really explain to all possible cases, but let me tell you this. So when you train your model, you have generally you have a test set, validation set, and the training set, right? So you have 3 sets, and you have performance metric for each set. If you want to get accuracy from training set, you can get it. If you want to get accuracy from validation set, you can get it. Of course, you can get accuracy from test set as well. Sometimes it happens that the performance from test set, the metrics higher than validation set, or other way around, the metrics lower in training set and higher in validation set. And then sometimes it's validation set, the performance is so high, and then your test set is really low performance, and it can have, there can be all kinds of cases here, right? Those are, if I use the analogy of programming, those are error message outputs that you can, when Python like give you error, it's not just only giving you error, but it's trying to explain where it hit the error, right? So the way that I see is that whenever I see those 3 different patterns, it kind of gives me an idea of what went wrong. And ideally, they are all similar to each other and they'll be the best, but that rarely happens. Okay, yeah, so.
That concept would be explained a little more France and talk.
And I'll just add one thing to that, right? I think the take-home message is that you should be highly suspicious of results that seem too good, right? And I think A, B, and C are very good. In most cases, when you get a result that's that good, it is either from data leakage, reverse causality, or the task was too easy, So, for example, if you are trying to predict um, mortality, right, and age is in your model, and you just take the general population. So actually, we're training a model right now for breast calcification as a predictor of cardiovascular disease. And it looked like it was doing really well, and then we stratified it by age, and the performance dropped quite a bit, because if age is in that model, age will obviously be the number one predictor of having a heart attack, right? More than anything else, right? So it is more like a flag for you to go back and investigate and make sure you don't have some obvious confounder or some obvious data leakage in your model. Not that it's necessarily a bad thing, right? But it's if it's too good to be true, it probably is.
I would add, be suspicious of every model you build, not just the good ones. Just be suspicious.
Any other questions? Yes.
Yeah, just by the fact that you are aware of it, that's actually start of a great practice. Yeah.
Yes.
Mustafa, that's why you're attending the summer school. So that you, at some point you will not be suspicious, or you're day one, Mustafa. So
I think I will answer that question with at least somewhat of a helpful answer, which is I think our job as model developers or statisticians or whatever is to be continually suspicious of the models that we build. And I think it's impossible to create a model that will be perfect in every scenario, but worse than that is being blind to the shortcomings or weaknesses of your model. We deal a lot in breast cancer, and the prevalence of that is even lower. I mean, our prevalence is less than 1% in our data set, right, for our breast cancer data set. I think the lesson here is not when do you start trusting your model. It's really of knowing the limitations and the circumstances under which you can trust and deploy the model, and the circumstances in which you can't. I don't know that you get to a point where you feel 100% confident. That's my take on it.
I agree with that.
Okay.
Yeah, and that's a big deal because of sort of like you can publish good papers, which is what we are observing, and publish in Nature, but that model is not usable. So rethinking how the downstream, how it's going to be deployed is going to be increasingly important for work to be actionable. Yes. So I would say that, to be honest, that we don't have a clear checklist of what is the acceptable model for that, right? So, and the reason for that, and I know that Theo, who is one of our postdocs, we've had quite a lot of discussions around this, and he's doing some similar work, which is to say, for example, in a radiology practice, maybe what I care about in the specific institution is the negative predictive value and the positive predictive value. If I have a case where I'm not sure, I want to know, is the model usually right or wrong? That's to me as an individual, right? But when you're deploying the AI for your institution, most people will maybe look at the sensitivity, like the overall metrics, but for the individual radiologist, those are two different metrics. So there's still today nothing that is very, very specific, I'd say, that says this is the right model and this is prime time. And so one of the initiatives you're involved in is called like the silent clinical trials, where you're watching the performance of the model, how it works going down. And Harry here leads the governance, the AI governance council for our department that is responsible for deciding which models, when should we deploy, when should we stop it, and maybe he can comment about it.
Yeah, it's a great question, and we should have a formal or informal discussion about it at some point. I can tell you a few steps that are definitely needed, right? The first is obviously you train and validate on internal data. The next is really to be useful, you have to be able to validate on external data. And the validation on external data is twofold. One is obviously, does the model generalize? But even before you get to that question, you have to see if the input data that you used and the way that your input data was structured and harmonized and curated can be repeated in an automated fashion at another place. So Saptarshi's example of harmonizing using a mapping table, just patient races, right? And let's say that's an input to the model. You go to another institution and their patient demographics are structured completely differently. Your model could perform perfectly fine here, and it could perform perfectly fine at another institution if theirs are mapped appropriately for that institution. But is that process generalizable? Can you devise a system in which at every institution you have a tractable way to get the input data into the right structure, format, harmonization, and curation to even be input into the model? Then you can think about generalizability, right? Before that, you can't even get to that. You can't even test that. The second important thing for clinical deployment is really what is going to be the downstream impact of this model. So what I mean by that is, I'll go back to the example of this breast vascular calcification model. So we have a segmentation model for vascular calcifications on mammography. Theo here has been working heavily on trying to validate that model as a predictor for cardiovascular disease outcomes, right? So we mined the clinical data. We determined when patients had a cardiovascular event, a soft event, a heart event, showed that their BAC score, their breast arterial calcification score, is predictive of cardiovascular disease or cardiovascular outcome, right? Now, that's fantastic. You can take that to the FDA and you can ask the FDA to validate the model for one of two things. You can either say that this model accurately segments vascular calcification, but we're not making a claim on what vascular calcification is clinically useful for. That's a distinction. This model will segment vascular calcification accurately with some performance metric. We are not making any claims on what vascalcs are useful for. Part two is this model will segment vascular calcifications, and we claim that these scores will then predict cardiovascular disease. Those are two entirely different questions. The second one is way harder to prove than the first one, right? So when we go to validate and get this model cleared, we're going to focus on the first one. Can we prove that it actually segments calcs properly? Then later on, we'll put out papers and publications for cardiovascular disease. Now, to actually answer your question, if the goal of this model is to screen women who are at risk of having a cardiovascular event, then what do you care about more? What do you think? Do you want it to be highly sensitive or do you want it to be highly specific? Sensitive, right? So you're okay with false positives because the implication of a false positive is a cardiology referral. And they check them out, they check their cholesterol levels, get them plugged into the system. It's really no harm to the patient. The answer to that sensitive versus specific question could be completely different. If you are going to use a model to predict whether or not to do a kidney transplant on a patient, you can't have a model with false positives, right? So there is no one size fits all answer to when is a model good enough for deployment. It really just depends on a case by case basis. But these are the thought process that you have to go through.
Awesome. Okay, so we came here for imaging. I had some people walked out and said, that there's a lot of content, But I hope that from